We've seen that the concept of planet habitability is a tricky one, because in the solar system, the Earth is clearly habitable, the only world we know of with biology on it, and yet there are a dozen or more places where there might be life, where all the ingredients exist, and there's enough energy to make it locally warm enough for liquid water to exist. Most of those places are in what's called the cryogenic biosphere, far from our Sun. We imagine that similar situations will also hold true in exoplanets. If we stick to a classical definition of habitability, it means the distance or range of distances from a Sun-like star where water will be liquid on the surface of a terrestrial planet. We've also seen that the presence of greenhouse gases alters this equation. On the Earth, the presence of greenhouse gases such as methane and carbon dioxide warms the Earth's surface by 30 degrees Celsius compared to what it would be in a vacuum. Similar situations will hold true of other planets, so they will be warmer than equilibrium temperature would suggest, based on the gases in their atmospheres. In the classic definition of a habitable zone, only the Earth is in the habitable zone of our solar system. Mars is too far away and therefore too cold. Venus is too close and therefore too hot for liquid water to exist. Similar arguments are used for the growing number of exoplanet solar systems being found. The broad issue of planet habitability is one under active research from biologists, geochemists, and planetary scientists. In fact, it's not clear the combination of factors that make the Earth habitable. How important is the Moon, for example? Its large size and proximity to the Earth stabilizes our axial tilt and prevents the axial tilt wandering over time, which would give us very extreme seasons and weather. How important are plate tectonics? Does a planet need to be large enough to generate geological activity and geochemical complexity? Plate tectonics are presumed to be important in the habitability of a planet, but in truth we don't know. If the Earth was originally a dry rock, how was the water delivered? And does the delivery mechanism involve both comets and asteroids? And how much does that depend on the particular attributes of a solar system? Is there a right amount of water for the Earth to have? We have a water planet, but not all the surface is covered in water. Is there a sweet spot in terms of the right amount of water? Remember, Europa is a water world in the outer solar system, completely covered by water and ice. What is the role of a large gas giant planet like Jupiter in our solar system and in maintaining the habitability of the Earth? Here, arguments go both ways. Some have argued that Jupiter is a protector, stopping a large intrusion of Earth-crossing asteroids that might cause mass extinctions, and others have argued that at some occasions, when the solar system becomes unstable, it sends debris our way. How important is the stability and tranquility of the star? Our Sun is a middle-aged, middle-weight star, but we can look for planets and life around other stars on the main sequence, doing what the Sun is doing, converting hydrogen to helium. Some of those stars are more active in their atmospheres, and perhaps that creates an unstable radiation environment that makes life more unlikely to develop. How important is the low eccentricity of the Earth's orbit, deviating from a circle by only 4%? We've seen that many of the first discoveries, and indeed the majority of exoplanets, have orbits that are more eccentric than the Earth's. So once again, their seasonal temperature variations and weather are more extreme than the Earth's. Does that mean that our planet is special and specially good for life? How important is a magnetic field? The Earth has an iron-nickel core and a relatively strong magnetic field. The magnetic field penetrates into space where it provides protection from the solar wind, a high-energy stream of particles and radiation that could be damaging to life on Earth. This is just a small sampling of the questions that people still have about what makes a planet habitable. And it will take research in a number of fields over a decade or more for us to solve the problem of habitability and decide which of the growing number of exoplanets may indeed be habitable. As we consider stars different from the Sun, the habitable zone moves in or out depending on the luminosity of the stars. Stars more massive than the Sun on the main sequence, converting hydrogen to helium, have shorter lives. Their habitable zones will be further out and include more real estate in terms of the orbits of potential planets. As we move to lower mass stars, their main sequence lifetimes are longer, and their habitable zones shrink in and become narrower, perhaps minimizing the number of possible planets in those regions. The second issue, as we vary the type of star around which we look for planets, is the lifetime of that star. We could look for planets and life around higher mass stars than the Sun, also converting hydrogen to helium on the main sequence. But those stars have substantially shorter lifetimes than the Sun does. For a star 3 times the mass of the Sun, that lifetime is 1 billion years or less. Perhaps that's not long enough for life or complex life to develop, and so should we turn our attention away from massive stars? Low-mass stars, on the other hand, give plenty of time for life to develop. A star with a tenth the mass of the Sun, which is an M-dwarf, will have a lifetime more than 10 times the lifetime of the Sun on the main sequence. That's 100 billion years. M-dwarfs will not die for a very long time, and there's plenty of time for biology to develop on any planets around those stars. However, if a planet is very close to a star in the habitable zone, it may be tidally locked to that star, which means, as the Moon does to the Earth, it will maintain one face towards the star at all times. That could create intense radiation soaking the surface of the planet. Perhaps the radiation redistributes through the atmosphere and circulation patterns, but we simply don't know. While Kepler has not taken data for long enough to find an Earth-like planet at an Earth-like distance from its star, with an orbital period of 300 or 400 days, it has found planets in the habitable zones of their stars, roughly 50. That number is rapidly growing and probably will be over 100 by the end of 2013. Many of these planets are close to their stars and on tight, hot orbits, but there is still the possibility of liquid water if they had rocky surfaces. Looked at in more detail, we can see that most of the planets Kepler has found so far are in the hot zone. They're in places too hot for liquid water to exist. But if we look at where the solar system lies in this diagram, we'll see that there are some planets strikingly similar to the Earth. So in addition to hundreds of Earth-like planets and 50 or more in their habitable zones, there are already a handful of Earth-like planets in habitable zones around their stars. Kepler is succeeding in its wildest and most ambitious goals. About a decade ago, it was realized that there's something called the M-dwarf opportunity. As mentioned, low-mass main sequence stars have very long lifetimes, enormous times for biology to develop. The second issue is that there are many more low-mass stars than high-mass stars. Perhaps 100 times as many stars a tenth the Sun's mass as stars like the Sun. This represents a huge opportunity for finding exoplanets, because even though the habitable zones around the M-dwarfs are slender and close to the star, if you add up the terrestrial or exoplanet real estate of those habitable zones, it outstrips the habitable zones around Sun-like stars. By some calculations, it could be orders of magnitude more real estate. And if exoplanets exist at all possible distances from their stars, that corresponds to a very large number of terrestrial exoplanets around red dwarfs that are in the habitable zones. A recent survey makes a projection of the census of Earth-like planets in the entire Milky Way galaxy, and finds that most of those Earth-like planets will be in orbit around M-dwarfs. With roughly 75 billion red dwarf stars in the Milky Way galaxy, a majority of the stars in fact, there could be 5 billion Earths in orbit around those M-dwarfs. Even if only a small fraction of those are in the habitable zones, that probably corresponds to hundreds of millions of habitable Earths in the Milky Way. But they're not in situations like this Earth. They're in orbit around dim, feeble, red-emitting stars. There's an additional concept in astrobiology called the Galactic Habitable Zone. This is pretty speculative, and some people disagree with the concept. The notion is that we should not be surprised, perhaps, that life exists on this planet around our Sun, about 2/3 the way out of the spiral galaxy, the Milky Way. Far out in a spiral disk of any galaxy like the Milky Way, fewer heavy elements are produced, and there's probably a zone at which not enough heavy elements are produced to make planets and biology. Going the other way, towards the center of the galaxy, the density of stars in space increases rapidly. And in the bulge of the galaxy and near the galactic nucleus, the densities can be hundreds or even millions of times denser than the solar neighborhood. This means that stars will come into close contact, or at least gravitationally interact, quite frequently, disrupting planetary orbits. A second consequence of high stellar densities is that the rare deaths of massive stars will be more frequent and more proximate to a habitable planet. That means that life may be hazardous because of the supernova rate being much higher than in the solar neighborhood. By this reckoning, the sweet spot for life in the Milky Way is an annulus, or a ring, extending from about 1/3 the way out from the center to 2/3 or 3/4 the way out from the center. This is not a hard enough argument to take as prescriptive for astrobiology. We simply don't know what the constraints are in the development of life elsewhere to put such strong bounds on it. The habitable zone is a traditional concept in astrobiology that may have outlived its usefulness, but it refers to the range of distances from a star where water can be liquid on the surface of a terrestrial planet. as being the place where life exists. We know from the solar system that there's likely to be habitability beyond this region in the cryogenic biosphere. Based on the traditional definition, however, Kepler is already succeeding in finding exoplanets in the habitable zones of their stars. Close to 100 have been found already, and a few of these are even Earth-like. Additionally, there's a concept of the Galactic Habitable Zone, whereby it's expected that life is more likely to form in the middle zones of the Milky Way and not too close to the edge or too close to the center.